In this video, we shall look at the so-called thin lens equation. This is an equation that governs the image formation of thin lenses. Broadly speaking, there are two kinds of lenses. The first one is known as the convex lens, with a shape like that. It is also known as a converging lens. The second kind is known as a concave lens, with a shape like that. And it is also known as a diverging lens. The reasons for the terms converging and diverging will be clear in a minute. Let's first look at the ray diagram of a typical converging lens. Now let's assume you have a lens like that. Of course, I'm exaggerating the thickness of this lens, but let's assume it's a very thin lens. Every ray diagram should have this horizontal line that passes through the center of that lens. This is known as the principal axis. Now let's assume you have a bunch of parallel light rays hitting the lens from the left, like that. Upon passing the lens, they will be converged at a particular point in a following manner, like that. Now this point, it's called the focal point of that lens, and this distance is called the focal distance, with an abbreviation f. Of course, if you insist on a third ray that is passing through the center of the lens, they will just go undeflected, straight. However, all the rays will converge at the focal point. And for that reason, such a lens is known as a converging lens. An important thing is that the focal distance for a converging lens is positive. And for that reason as well, these are known as positive lenses. Now let's look at a diverging lens. Let's first sketch a typical ray diagram. So this is the principal axis. Now let's sketch a bunch of light rays that are parallel to the principal axis. And what's going to happen to them? They will be diverged like that. So if you have one more here, it will be diverged like that. Now assume there is another ray of light that is on the principal axis passing through the center of that lens. It will just go like that. So how do you determine the focal point? The focal point can be determined by extrapolating the diverging rays backward, like that, for all the rays, like that. So this point here, where all the rays seem to diverge from, is called the focal point. And the distance between the focal point and the center of that lens is called the focal distance or the focal length. Now in this case, the focal length, f, is a negative number, and for that reason, it is called a negative lens. Before we write down the thin lens equation, let's begin analyzing image formation for a converging lens and the important variables that show up in thin lens equation. Now let's assume that you have an upright object. So this is the object. Now the distance between the object and the center of the lens, let's denote it with p. P is called the object distance. The question is, where is the image of this object? So let's construct the ray diagrams. The first ray that you want to use is the parallel ray that will converge towards that focal point, like that. The second ray is the one that passes through the center of the lens undeflected, like that. The point where they meet is where the image is. And now the image, of course, will extend from the principal axis to that converging point. And that's your image. And the distance between the center of that lens to where the image is called the image distance. We shall denote it with the letter Q, image distance. And of course, that distance there is the focal length or focal distance of that lens. Thin lens equation connects P, Q, and F in a following manner. 1 over F equals 1 over P plus 1 over Q. So you see, if you know the focal length of the lens, and if you know where the object is, you can predict where the image will be. As you can see, this is an inverted image. And it is also known as a real image, because light actually passing through the image. And you can actually project this image on a screen. Another pair of important variables are the height of the object and the height of the image, because the ratio of height of the image to the height of the object is known as magnification. And this magnification can also be expressed in terms of P and Q in a following manner: minus Q over P. So this minus sign is important, as you will realize later. Now let's look at the image formation for a concave lens. So we use two rays in order to pinpoint the position of the image. This is the object. So the first ray is usually the one that is parallel to the principal axis, which will be diverged in that manner, and you can extrapolate it all the way to focal point, like that. The second ray that we shall use is the one that is passing through this center of that lens undeflected, in that manner. The point where they cross is where the image is. In this case, it's right there. So that is the image. And as you can see, the image is an upright image. And because light is not actually passing through that image, because this is the extrapolation, it's known as the virtual image. Let's look at the parameters. That is the object distance. This is the focal length. And that distance is the image distance. And they are related through the thin lens equation, like that. And if the size of the image is hi, the magnification is given by hi over ho, which is also minus q over p. Next, we shall look at sign conventions to determine the signs of hi, h naught, q, p, and f. Let's first determine the sign for the focal length. If you're dealing with a convex lens, then the focal length is positive. If you're dealing with a concave lens, then the focal length will be negative. Now the sign convention for object distance. If the object is on the incoming side of the surface, meaning if the object is, let's say, here. So this is the incoming side and this is the outgoing side, because this is where the rays are incoming towards the lens and this is the outgoing away from the lens. So if the object is on the incoming side of the surface of the lens, then the object distance is positive. The same goes for this lens. If the object is here, it is on the same side as the incoming side of the surface, then the object distance is positive. Now what about the image distance? If the image is on the outgoing side of the surface, then it's a positive number, meaning if your image is like this, in the example that we discussed a few minutes ago, then it's positive. If the image is on the incoming side of the surface of the lens, then it will be negative. For example, in a case where you have a concave lens where the image was formed like that. So in that example, Q is negative. Now, the sign convention for H. That refers to the size of the object and the size of the image. If they are upright, like that, then H is positive. If they are inverted, meaning like that, then H is negative. And you see the sign for the magnification will be determined accordingly from P, Q, or HO and HI, the height of the object and the height of the image respectively. Let's look at the following problem. A converging lens of focal length 10 cm forms images of an object. Find the nature of the image and where the image is when the object is at distance of 28 cm from the lens, and also find its magnification. Now the focal length is 10 cm. The object is there, and that distance is 28 cm. So we have rays of light going like that and like that. So the image is formed here, and that is the image distance Q. So the thin lens equation is 1 over F equals 1 over P plus 1 over Q. Now this is a convex lens, so F is positive. F is 10 cm, so 1 over 10. Now we note the object is on the incoming side of the surface, so P is also positive, 1 over 28, and you can solve for the Q. And when you do that, you get Q as 15.6 cm. Now you see this is positive, and it agrees with the fact that the image is formed on the outgoing side of the surface. Because light is passing through the image, it's a real image, and as you can see, it's inverted. The magnification in this case is minus Q, which is 15.6, over P, which is 28, and that's going to give you minus 0.56, a number which is less than 1. That means the size of the image is less than the size of the object. Now let's do part B. Repeat when the object is at 10 cm from the lens. So now the object is at 10 cm from the lens. We know the focal length is also 10 cm. So immediately you see that from the thin lens equation, since F is positive 10, now P is also positive 10 because the object is on the same side as the incoming surface, and that would make Q to be infinity, or the image is formed at infinity. Similarly, the magnification becomes infinite as well. Now part C, repeat when the object is at 6 cm from the lens. So now the object is here, and the distance is 6 centimeters. So let's construct the first ray like that, and the second ray through the center of the lens like that. And you see the image cannot be formed here, but it's formed there, and it is an upright image. And let's determine Q. So 1 over F, F is positive, which is 10 cm, equals 1 over P, P is also positive, 6 cm, plus 1 over Q. And Q will be minus 15 cm. The minus sign agrees with the fact that the image is at the incoming side of the surface and not the outgoing side of the surface. Now what about the magnification? The magnification is minus Q over P, so minus 15 is plus 15, and P is 6. And you get 2.5 for the magnification. Another property of that image is that it is a virtual image, because the position of the image is determined from extrapolation and there is no light passing through it. Thank you for watching.